Every year, factories worldwide churn out more than 430 million metric tons of plastic. That's enough material to fill a line of freight trains wrapping around the entire globe 7 times over. And here's a figure that might surprise you. Less than 10% of all the plastic ever manufactured has actually been recycled. The remainder ends up scattered across landfills, drifting through oceans, and even lodged inside our own bodies. Researchers have detected microscopic plastic fragments in human blood, lungs, and arteries. A substance that took over the planet within a single century is now quietly accumulating inside us. But in October 2025, a modest team of researchers at a forestry university in northeastern China published findings that made the engineering world stop and pay attention. They announced they'd developed a completely new type of plastic, made entirely from bamboo. Not a blend of bamboo and petroleum. Not a partial substitute. A fully 100% bamboo material that's stronger than conventional plastic, compatible with existing factory equipment, and fully decomposes in ordinary soil within 50 days. If you enjoy videos covering breakthroughs that rewrite the rules of entire industries, hit that like button. These videos take considerable effort to produce, and subscribe so you don't miss what's coming next. The significance runs far deeper than a single new material. To understand why engineers are calling this remarkable, you need to understand how plastic conquered the world, why every previous attempt to replace it has failed, and what makes this bamboo discovery so fundamentally different from everything before it. Think about the phone resting in your pocket, the container holding last night's leftovers, the casing wrapped around your laptop, the dashboard inside your car. They all share something in common. They're all made of plastic, and that's no coincidence. Plastic spread everywhere because it accomplishes things no other material can replicate. It melts and pours into virtually any shape imaginable: a bottle, a gear, a car bumper, a tiny clip buried inside medical equipment. It costs almost nothing to manufacture. It doesn't rust like metal, rot like wood, or shatter like glass. It keeps water out, contains electricity safely, and survives being dropped, heated, or left outside in the rain. The medical field alone depends on plastic in ways most people rarely consider. Every syringe, every IV bag, every sterile wrapper protecting surgical tools from contamination. Without plastic, modern hospitals would struggle to function. Food storage relies on it equally. Plastic wrapping keeps bread fresh for weeks instead of mere days. It lets food travel across continents without spoiling. So when someone suggests simply eliminating plastic altogether, the real question becomes, what else can accomplish all of that while costing next to nothing to produce? So far, the honest answer has been nothing, and that's precisely why replacing plastic has proven so difficult. You're not merely swapping one material for another. You're attempting to replace something holding together the entire framework of modern civilization. Removing plastic would resemble pulling every nail out of every building throughout an entire city. Everything looks fine until you actually try it, and then everything comes crashing down. But there's a catch, and it's significant. The exact quality making plastic so useful is the same quality making it dangerous. It doesn't break down naturally. A plastic bottle discarded today will still sit inside a landfill hundreds of years from now, outlasting you, your children, and their children too. Rather than disappearing, it gradually fragments into smaller and smaller pieces, too tiny to see, yet small enough to infiltrate everything. Those microscopic fragments end up in rivers, in soil, and, as researchers are now discovering, inside the bodies of living creatures. Fish swallow them, birds consume them, and humans breathe them in or ingest them through food and water. The material we built our entire world around is now turning up inside us, and nobody fully understands what that means for human health yet, so the world finds itself stuck. We constructed everything around a material that never disappears, and every year we manufacture even more of it. The need for something better isn't simply about environmental kindness. It's about the fact that plastic is now embedded inside our bodies, a problem that won't resolve itself. But solving this has proven far harder than anyone initially anticipated. Every single attempt at creating a replacement has hit the identical wall. The bioplastics industry has spent decades attempting to fix this exact problem, and nearly every time it's failed the same fundamental way. The materials produced are either strong but refuse to decompose, or they decompose but prove too weak structurally, or they accomplish both but cost too much to manufacture at meaningful scale. The most well-known bioplastic is called PLA, short for polylactic acid, made from fermented cornstarch. It can decompose, but only inside a specialized industrial facility maintaining temperatures above 58 degrees Celsius for weeks at a stretch. Toss a PLA cup into your backyard garden or a regular landfill, and it'll simply sit there for years, looking and behaving exactly like conventional plastic. PLA carries additional drawbacks too. It fractures easily when dropped. It can't withstand high heat. And it's manufactured from corn, meaning valuable farmland gets diverted toward growing plastic instead of food. Growing corn specifically for plastic production, while people worldwide struggle to access adequate food, isn't a sustainable plan for the entire planet. Another alternative is called PHA, short for polyhydroxyalkanoate. It decomposes more readily than PLA, promising in theory, but costs several times more than conventional plastic, because manufacturing it requires a complex bacterial growth process. When something costs 5 times more than what it's replacing, companies simply won't purchase it. PHA has remained confined to producing tiny quantities for specialized applications for years. Starch-based plastics carry their own distinct problem. They dissolve in water, meaning you can't use them for anything that might get wet. Cellulose acetate proves considerably stronger, but manufacturing it requires harsh chemicals, somewhat defeating the entire purpose of creating something environmentally friendly. Every single approach hit the identical wall. You could engineer something strong. You could engineer something biodegradable. You could engineer something affordable. But nobody managed to combine all 3 qualities simultaneously. The core problem wasn't a shortage of good ideas. The problem was chemistry at its most fundamental level. Nobody had figured out how to take plant-based material and restructure its building blocks into something functioning like plastic, without introducing chemicals that ruin the entire point of going green. Picture attempting to transform a pile of wood into a steel beam. You know the wood sits right there. You know steel exists as a possibility. But you can't simply bend the wood into a new shape and call it steel. You'd need to fundamentally alter what the wood actually is at the molecular level. And nobody understood how to accomplish that transformation with plant materials destined to become plastic. That's precisely the wall the research team in Harbin, China, just shattered. And the method they used is what left engineers worldwide stunned. This particular research emerged from a place nobody expected. It wasn't a massive oil corporation. It wasn't a Silicon Valley tech startup. It wasn't some classified government laboratory. It came from Northeast Forestry University in Harbin, China, an institution primarily focused on studying trees and forest science. The lead researchers, Haiping and Dawei Zhao, collaborated alongside a team from Shenyang University of Chemical Technology. Together, they decided to attempt something with bamboo that most materials scientists had abandoned years earlier as hopeless. Here's why bamboo proved so notoriously difficult to work with. Bamboo's primary structural component is something called cellulose, the substance giving plants their shape and structural strength. It's present inside every tree, every leaf, every single blade of grass. Within bamboo specifically, cellulose molecules are locked together through microscopic connections called hydrogen bonds. These bonds are remarkably strong, allowing a bamboo stalk to stand tall and support significant weight even during powerful windstorms. But those identical bonds are precisely what make bamboo so resistant to reshaping into anything else entirely. The cellulose stays rigidly fixed in place. You can't simply melt it and pour it into a mold the way you would with conventional plastic. Attempt forcing bamboo into a new shape, and it snaps and fractures rather than bending cooperatively. Other researchers had previously attempted creating bamboo-based plastic, but they always relied on shortcuts. They'd mix ground bamboo fibers together with conventional plastic adhesive. The bamboo contributed some structural strength, but the plastic adhesive held everything together structurally. The resulting material was essentially half bamboo, half petroleum, a blend rather than a true replacement. And because it still contained that plastic adhesive component, it didn't actually decompose properly in nature. Wu and Zhao pursued something entirely different. Rather than mixing bamboo with plastic, they transformed bamboo directly into plastic itself through two steps that proved simultaneously simple and remarkably clever. Step 1. They soaked the bamboo cellulose inside a specialized liquid solution composed of zinc chloride and formic acid. This particular liquid breaks apart the hydrogen bonds holding the cellulose molecules rigidly in place, yet doesn't damage the molecules themselves in the process. Picture carefully untangling knots within a fishing net. The net remains fully intact. The string retains its strength. It's simply no longer bound into that rigid fixed shape anymore. Step 2. They introduced ethanol into the mixture. The ethanol functions like a guide molecule, helping the newly loosened cellulose molecules locate each other and reconnect in an entirely fresh configuration. As they reconnect, they form new bonds even stronger and tighter than the original bonds found naturally in bamboo. The molecules essentially rebuild themselves into something structurally superior. The resulting material looks, feels, and behaves exactly like conventional plastic. But it's manufactured entirely, 100%, from molecules that already existed inside the original bamboo. No plastic adhesive got added. No petroleum-based chemicals got mixed in. No toxic waste byproducts got left behind. They named this new material BM plastic, short for bamboo molecular plastic, a name describing both its origin and its manufacturing method simultaneously. But a clever name and compelling backstory mean nothing without actual performance numbers backing them up. And those numbers are precisely what stunned the engineering community. Plenty of materials look impressive inside a laboratory setting, yet most fall apart the moment you attempt using them in real-world applications. BM plastic didn't follow that pattern. Its testing results proved so strong that engineers who'd spent entire careers working exclusively with conventional plastic had to take this material seriously. A material originating from a forestry school outperforming petroleum-based plastic in strength testing isn't something anybody expected walking in. The strength figures proved difficult to dismiss. BM plastic withstands a pulling force of 110 megapascals, roughly twice as strong as PLA, the corn-derived bioplastic. It also outperforms high-impact polystyrene, a common plastic used throughout countless everyday products. To put that figure into perspective, 110 megapascals approaches the strength level of certain steel and aluminum alloys used inside cars and aircraft. This isn't some flimsy plant-based plastic that cracks if you glance at it wrong. It's a real structural material capable of bearing real weight. It also resists bending remarkably well, scoring 6.41 gigapascals in bending tests, essentially meaning it won't warp or sag under applied weight. It actually outperformed ABS plastic in this test, the tough plastic used in car dashboards and Lego bricks. If you've ever stepped barefoot on a stray Lego piece, you understand precisely how durable ABS truly is. Heat resistance formed another significant test category. BM plastic maintains its structural shape at temperatures exceeding 180 degrees Celsius. Researchers left samples inside 100-degree heat for 7 consecutive days, without any cracking whatsoever. They also submerged samples in strong acid, and the surface remained completely undamaged. Attempt that same test with a PLA cup, and it would warp, crack and disintegrate within days. BM plastic simply sat there, entirely unaffected. The material also absorbs substantial energy before fracturing. Scientists refer to this property as work of fracture, and BM plastic scored 80 kilojoules per cubic meter, outperforming both conventional plastic and most commercial bioplastics currently on the market. Stated plainly, it withstands real impact without shattering apart. That property matters tremendously for applications like car components, phone casings, tool handles, and anything prone to being dropped or bumped accidentally. Then came the figure attracting the most attention from environmentally conscious observers. BM plastic, completely decomposed in ordinary soil within approximately 50 days. Not inside a specialized industrial facility, not within an industrial composting system, just buried in plain dirt, similar to a leaf falling from a tree, and gradually returning to the earth naturally. Here's something even more remarkable still. When researchers recycled it using that identical liquid processing method, the recycled material retained approximately 90% of its original structural strength. Conventional plastic grows progressively weaker with each recycling cycle, precisely why recycled plastic typically ends up manufactured into low-value products like park benches. BM plastic doesn't suffer from that limitation. You can recycle it repeatedly, and it remains nearly as strong as the day it was originally manufactured. The research team published all their underlying data publicly within a paper appearing in Nature Communications. They disclosed every test result, every numerical figure, every processing step involved, allowing the entire scientific world to independently verify their work. But all those impressive numbers wouldn't matter much if the raw material couldn't support manufacturing at massive scale. And that's precisely where bamboo carries an advantage almost no other plant can realistically match. Selecting bamboo specifically wasn't random. You can't simply substitute any other plant and expect identical results. Bamboo carries a unique combination of properties, making it ideally suited for this application. And equally important, it already possesses a supply chain that's fully established and immediately ready to scale. Bamboo grows faster than any other plant found anywhere on Earth. Certain species can grow more than a full meter within a single day, not a typo. You could watch it grow if you sat still long enough. And after cutting it down, it regrows directly from the same root system. You don't need to plant fresh seeds, clear additional land, or install irrigation infrastructure. A bamboo forest fully regenerates within 3 to 5 years after harvesting. Compare that timeline against a pine tree, requiring 25 to 30 years to reach appropriate size for cutting. And while corn crops must be replanted entirely from scratch annually, bamboo simply keeps regenerating naturally on its own, repeatedly. Bamboo also produces roughly 5 times more plant material per hectare, compared with conventional timber forests. It pulls carbon out of the atmosphere as effectively as, or even more effectively than, many tree species. And it thrives on land unsuitable for conventional farming, meaning it doesn't compete with food crops for valuable agricultural space. This matters significantly since corn-based bioplastics like PLA face criticism precisely for consuming farmland that could otherwise grow actual food. China possesses the largest bamboo resources found anywhere globally. More than 7.5 million hectares of bamboo forests spread across roughly 20 separate provinces. The country hosts over 500 distinct bamboo species. China's bamboo industry already generates close to 320 billion yuan annually and supports more than 7.5 million farmers whose livelihoods depend directly upon it. That means the entire infrastructure for growing, harvesting, transporting, and processing bamboo already exists at massive scale. Nobody needs to construct these systems from nothing. This matters considerably more than it might initially appear. Many promising new materials fail not because they don't function properly in laboratory settings, but because nobody can manufacture enough of them affordably. If your remarkable new material requires some rare plant growing exclusively within one small geographic region, you'll never produce enough to meaningfully replace hundreds of millions of tons of conventional plastic. But bamboo grows across the entire world, found throughout massive regions spanning Asia, Africa, and South America. The world contains roughly 22 million hectares of bamboo forests total, distributed across numerous different countries. Bamboo already gets harvested at enormous scale for building materials, furniture, flooring, paper, and textiles. The supply chain already operates actively throughout many regions worldwide, meaning companies wouldn't need to construct an entirely new system from the ground up simply to start utilizing bamboo plastic. So bamboo represents one of the exceedingly rare materials simultaneously excellent for manufacturing strong plastic, and already available in enormous quantities right now. It combines the performance characteristics, the raw supply, and the established farming infrastructure all together into one complete package. But possessing the right plant material and correct chemistry still isn't sufficient by itself. The real question becomes whether you can actually manufacture this material inside conventional factories, using machinery that already exists. Achieving impressive laboratory results represents one accomplishment. Manufacturing something inside an actual factory, using real production machinery, represents an entirely separate challenge. This is precisely where most bioplastics ultimately fail. They require specialized equipment that conventional factories simply don't possess. BM plastic doesn't suffer from this limitation. It runs through injection molding machines, the identical equipment manufacturing most plastic products found throughout the world today. It can be cut, drilled, and shaped using standard tools. It presses into flat sheets or complex three-dimensional shapes without difficulty. Researchers demonstrated this practically by manufacturing lampshades, gears, packaging containers, and decorative items, all produced using existing machinery without any modifications whatsoever. This detail proves significant. Most emerging bioplastics require entirely new factory production lines, specialized molds, or operating conditions that conventional plastic factories simply cannot accommodate. That means companies would need to invest millions before manufacturing even a single product. BM plastic skips that expensive step entirely. If you already own an injection molding machine, you could theoretically start manufacturing bamboo plastic products tomorrow. The manufacturing process also operates at room temperature, which matters considerably. Heating plastic represents one of the largest expenses involved in manufacturing it. Conventional plastic factories rely on massive ovens and enormous heaters to melt their raw material. BM plastic requires none of that infrastructure whatsoever. No scorching kilns, no pressurized tanks, no giant industrial ovens. That eliminates substantial energy costs entirely. The chemicals involved, zinc chloride and formic acid, are common and inexpensive. The ethanol can be collected and reused repeatedly. Nothing throughout the entire process requires rare or expensive materials. Researchers estimated manufacturing BM plastic would cost approximately $2,300 per ton. Conventional plastic costs roughly $1,200 per ton currently, nearly double, which initially sounds problematic, but two factors narrow that gap considerably. First, costs will inevitably decrease as production scales up and becomes more efficient. Second, that $1,200 figure for conventional plastic doesn't account for the damage it actually causes. Factor in pollution cleanup costs, health complications from microplastic exposure, and emerging government penalties. And the actual cost of conventional plastic could reach $2,400 per ton by 2040, according to one recent study. The response to this material has moved remarkably fast. China has actually been preparing for this moment for several years already. Back in 2022, the government launched an initiative specifically targeting bamboo as a plastic replacement. In 2023, they released a comprehensive 3-year action plan. Real products are already reaching markets. Bamboo fiber tableware exports increased 35% throughout 2025. Bamboo piping is being installed throughout cities, replacing traditional steel and concrete infrastructure. A bamboo-based drone even successfully flew, with bamboo comprising 25% of its overall body structure, weighing 20% less than comparable carbon fiber, while costing roughly a quarter as much to produce. Meanwhile, global negotiations surrounding a plastics treaty collapsed entirely in 2024. Participating nations couldn't reach agreement on reducing plastic production levels. The underlying message proved unmistakable. Don't wait around for regulations to solve this problem. Whichever countries and companies develop the replacement first will ultimately dominate the market. Real challenges remain though. BM plastic is inherently rigid, excellent for solid structural components, but unsuitable for flexible applications like plastic wrap or thin bags. It needs to reliably last for years during active use, before eventually decomposing after disposal, and that particular balance still requires additional refinement. Scaling production from laboratory quantities toward manufacturing millions of tons represents a massive undertaking demanding considerable time and capital investment. But no bioplastic developed previously has ever successfully combined this level of structural strength, this kind of complete decomposition, this degree of recyclability, this level of manufacturing compatibility, and this scale of available raw supply, all simultaneously within one single material. The world required an entire century to build its dependence on conventional plastic. That dependence won't disappear overnight. But for the first time, there now exists a material offering superior performance alongside real sustainability within one combined package. It doesn't ask companies to sacrifice something valuable. It offers something demonstrably better instead. And that's precisely what meaningful change actually looks like. If this video shifted how you think about something you touch dozens of times daily without ever considering its origin, give it a like and subscribe for more content like this. Turn on notifications so you never miss what comes next. Here's a question worth pondering. If a grass growing a meter per day was sitting there all along as the answer to our plastic crisis, what other solutions do you think remain hidden throughout nature, simply waiting for someone to finally ask the right question? Let me know in the comments.